There is a particular kind of darkness that exists just before sunrise in the Ozark Mountains. It is not the flat, featureless dark of a windowless room. It is a layered darkness, deep blue at the zenith, shading toward a bruised purple at the horizon, with the black silhouettes of oak and hickory and shortleaf pine rising against it in long, irregular lines. The air is cool and very still. The forest floor holds the night's moisture in small pockets of mist that drift between the tree trunks like slow, white breath. Somewhere below the ridge, a spring is moving. You can hear it faintly, a soft and patient sound, water over limestone, continuous and unhurried. The Ozark Plateau stretches across southern Missouri and northern Arkansas, extending into the corners of Oklahoma and Kansas, a broad, ancient, deeply eroded upland of extraordinary geological complexity. From above, from a hillside or a fire tower, the landscape looks peaceful and familiar. Forested ridges rolling away in every direction, cedar glades on the south-facing slopes, their pale limestone outcrops catching the first light, creek bottoms winding through the valleys, their water clear and cold even in the middle of summer. But beneath the surface of these peaceful hills, something else entirely is happening. Beneath the forest floor, beneath the thin soil and the root systems of 10,000 trees, beneath the limestone bedrock itself, the earth is hollow. Not everywhere, and not in the way of empty space so much as in the way of passages and chambers and galleries and rivers, a three-dimensional labyrinth of carved and dissolved and fractured stone that extends for distances that have not yet been fully measured. The Ozark region contains one of the largest karst landscapes in North America. Hundreds of caves have been documented here. Thousands of springs emerge from the rock, many of them fed by underground rivers that travel for miles beneath the surface before breaking into the light. Sinkholes dimple the meadows and the forest floors in numbers so great that in some areas they become the dominant feature of the landscape, the surface world defined as much by its absences as by its presences. And within this underground network, within its rivers and chambers and long, winding passages, there is something that has puzzled and fascinated every person who has ever descended into it with a lamp and an open mind. There are passages that look almost designed. Corridors that run straight for distances that seem too great for accident. Chambers with flat floors and domed ceilings that call to mind the word architecture before the word geology arrives. Right-angle turns, parallel passages separated by walls of uniform thickness. Spaces that, in the torchlight or the beam of a headlamp, seem to carry the suggestion of intention, of planning, of purpose, of a mind that wanted them to be exactly as they are, which raises a question. A genuine question, one that geologists and cave scientists have considered carefully, one that has no quick or simple answer, and one that we are going to spend a long time with tonight. Why do some underground passages appear almost designed, even though geology may tell a very different story? Welcome to History's Sleepy Time. Tonight we are going underground into the Ozark Plateau, slowly and carefully, and with great respect for both the science and the mystery. We are going to follow the water that carved these passages over hundreds of millions of years. We are going to walk beside the ancient peoples who sheltered in the bluffs and the caves of this landscape. We are going to meet the explorers and geologists who mapped what they found here, and we are going to sit with the remarkable question of what it means when nature produces something that looks, by every instinct, like the work of a purposeful mind. Before we go any further, if you are watching History Sleepy Time for the first time tonight, welcome. We would love it if you took just a moment to like this video and subscribe. And please leave a comment and let us know where you are watching from. Whether you are in a cabin in the Ozarks, or a city apartment far away, or somewhere in the world that surprises us entirely, we always love to know. Now, let us go into the stone. The first light of morning catches the top of the ridgeline to the east. The color is pale gold, not yet warm, more like the color of old limestone than of fire. It spreads down the hillside slowly, filling the spaces between the trees with a thin, clear radiance that burns the mist off the low ground in slow curls of white vapor. A wood thrush begins to sing, a single, liquid phrase, then silence, then the phrase again. The forest wakes around it, bird by bird, tree by tree, and somewhere below all of this, below the singing bird and the morning light and the mist and the limestone outcrops glistening with dew, the underground rivers are still moving. They have been moving since long before there were birds to sing above them. They will be moving long after the morning is gone. We follow the water down. To understand the Ozark Labyrinth, you must begin not with caves and not with underground rivers, but with an ocean. An ocean that no longer exists. An ocean whose shores no living creature ever saw, because the creatures alive at that time were the kind that had not yet developed the capacity for sight. An ocean that covered not just the region we now call the Ozark Plateau, but much of the interior of the North American continent, in a warm, shallow, tropical sea that teemed with life in every form the Paleozoic era had to offer. The Paleozoic era, the first great chapter of complex animal life on Earth, lasted from roughly 540 million years ago to about 250 million years ago. For much of this vast span of time, the interior of North America was submerged beneath shallow seas. The region that would eventually become the Ozark Plateau sat near the equator during these ancient periods, covered by warm, clear, mineral-rich water, the kind of water in which carbonate-secreting organisms thrive. And those organisms were everywhere. Brachiopods, shell-bearing animals that filtered food from the water. Crinoids, elegant, flower-like creatures that anchored themselves to the seafloor and spread their feathery arms into the current. Bryozoans, colonial animals that built intricate, lace-like structures of calcium carbonate. Corals, already ancient in their form. Trilobites, moving across the seafloor in their segmented armor. And countless smaller creatures, the microorganisms of the ancient sea, each one contributing its tiny shell or skeleton to the accumulating sediment below. When these creatures died, and they died in uncountable numbers, over hundreds of millions of years, their shells and skeletons settled to the seafloor. Layer upon layer of calcium carbonate, compressed by the weight of new sediment above it, gradually cemented into rock. The process is slow by any human standard, but it is inexorable. Over time, the kind of time that makes a million years seem like a passing moment, those accumulated shells became limestone. Dense, pale gray-white rock, laced with fossils, stratified in horizontal layers that record the conditions of the ancient sea with extraordinary fidelity. Much of the Ozark region is underlain by limestone, but it is also underlain in significant quantities by a closely related rock called dolomite or dolostone, which forms when the calcium in limestone is partially replaced by magnesium, usually through the action of magnesium-rich groundwater moving through the rock after it has solidified. Dolomite is harder and somewhat less soluble than limestone, but it is still susceptible to dissolution by acidic water, and it plays an important role in the development of the Ozark karst landscape. The transition from ocean floor to upland plateau required several more extraordinary geological events. The seas eventually retreated. The causes were complex: changes in the global configuration of continents, shifts in sea level, tectonic events. But the result was that the accumulated limestone and dolomite of the Ozark region emerged from the water and became land. And then, over the subsequent hundreds of millions of years, it was uplifted. The Ozark Plateau is, in geological terms, a broad structural dome, a region where the underlying rock layers have been gently bowed upward by tectonic forces, creating a high central area that has been subject to erosion for an immensely long time. The St. Francois Mountains in southeastern Missouri represent the ancient core of this dome, some of the oldest exposed rock in the central United States. Igneous rocks formed deep in the earth and now exposed at the surface by the erosion of the younger sedimentary layers that once covered them. Around this ancient core, the Paleozoic limestone and dolomite layers dip gently outward in all directions, forming the broad, dissected upland that most people recognize as the Ozarks. Uplift and erosion are partners. As the Ozark Dome rose, the streams and rivers flowing across it began to cut downward, eroding their valleys deeper and deeper into the rock, exposing new surfaces, carving the dramatic bluffs and hollows and creek valleys that characterize the Ozark landscape today. The Buffalo River in Arkansas cuts through hundreds of feet of Paleozoic limestone and dolomite, exposing walls of stratified rock that record, layer by layer, the conditions of seas that have not existed for hundreds of millions of years. But erosion and uplift alone do not create the Ozark karst. For that you need chemistry. The same process that shaped Mammoth Cave in Kentucky operates here, across a much broader and in some ways even more complex landscape. Rainwater absorbs carbon dioxide from the atmosphere and from the soil, becoming mildly acidic. This acidic water, a weak solution of carbonic acid, moves downward through the soil and into the fractured limestone and dolomite below, and it dissolves the rock, not quickly, not dramatically, but persistently and without stopping, over timescales that stretch the imagination. The Ozark Plateau has been above sea level and subject to this dissolution process for a very long time, long enough for the karst landscape to develop to an extraordinary degree of complexity. The result is visible everywhere on the surface. Sinkholes, large and small, scattered across the uplands like the dimples left by slow rain in soft earth. Springs, thousands of them, emerging from the base of bluffs and hillsides where underground water finds its way back to the surface. Losing streams, which flow on the surface for a while and then simply disappear into sinkholes or seeps, continuing their journey underground. Dry valleys, carved by ancient streams that have since been diverted underground, their surface channels abandoned and empty. And beneath the surface, the caves. The cave systems of the Ozark region are numerous and varied. Some are relatively small, accessible through a single entrance, and explored fully in an hour. Others are vast, extending for many miles through the rock, with multiple levels of passage corresponding to different positions of the water table in the past, with underground rivers still flowing in their deepest sections, with formations of great age and beauty in their dry upper levels. The Salem Plateau, which covers much of the central Ozark region in Missouri, is underlain by some of the oldest and most cavernous limestone in the area, rock that has been subject to dissolution for an immensely long time, and that contains cave systems of corresponding complexity and scale. Ozark National Scenic Riverways in Missouri protects a stretch of river corridor notable for its extraordinary density of springs, many of them fed by extensive underground cave systems in the surrounding karst. The Buffalo National River in Arkansas passes through a landscape of Paleozoic bluffs and karst features that represent some of the finest examples of Ozark geology anywhere in the region. The Ozark Plateau is not one place, geologically speaking. It is a mosaic of different rock types, different ages, different degrees of karstification, different hydrological systems. Understanding its underground world requires understanding this complexity, the way the limestone layers grade into dolomite, the way ancient faults and fractures in the rock have influenced the direction and character of underground water movement, the way the regional water table has changed over geological time in response to ongoing erosion and the slow deepening of the river valleys. It is this complexity, geological, hydrological, and structural, that we need to carry with us as we go deeper. Because the features of the Ozark Labyrinth that appear, to the human eye, most like deliberate design, are in most cases the direct expression of this geological complexity, of the way water interacts with rock that has been fractured and faulted and stratified in very particular ways. The stone that became the Ozark Labyrinth was made by an ocean. It was shaped by time, and it was carved from the inside by water. Always the water. Consider for a moment the journey of a single raindrop. It falls from a cloud somewhere above the Ozark uplands, above a cedar glade, perhaps, or a meadow on the flat top of a ridge. It strikes the thin soil, and if the soil is already saturated, as it often is after a period of sustained rainfall, it begins to move across the surface, joining other drops, forming a thin sheet of water that flows toward the nearest low point. That low point might be a sinkhole, a rounded depression in the ground, perhaps filled with leaf litter, perhaps grassy around its edges, its bottom sometimes wet and sometimes dry depending on the season. The water enters the sinkhole and disappears. From the surface, it seems to simply vanish, to be absorbed by the earth, gone, but it has not gone anywhere in the most important sense. It has simply changed its medium. It has entered the karst system, and it is now moving underground, through cracks in the limestone, through widened joints, through the conduits and passages of the cave network below, and it will eventually, somewhere downstream, emerge at a spring. That journey from raindrop to spring through the underground might take hours or days or weeks, or in some cases much longer. The time depends on the nature of the passage it travels through, the distance to the spring, and the rate of flow. Some springs in the Ozark region respond very quickly to rainfall events, their flow surging within hours of a heavy rain, their water temperature rising slightly as recently fallen surface water reaches them. Others respond more slowly, their flow sustained by water that has been moving through the aquifer for a much longer period, mixed and buffered by the enormous storage capacity of the karst system. The science of how caves form, speleogenesis, to use the technical term, is one of the most fascinating chapters in geology, and it is directly relevant to understanding why the Ozark Labyrinth looks the way it does. Cave formation in a karst landscape like the Ozarks begins, almost always, with fractures in the rock. Limestone and dolomite, like most rocks, are not monolithic. They are cut by systems of joints and fractures, planes of weakness in the rock created by tectonic stress. By the expansion and contraction of the rock mass over geological time, and by the way the rock was deposited and subsequently deformed. These fractures are the initial pathways for groundwater, the routes along which slightly acidic water first begins to move through the rock, dissolving it along the way. The pattern of fractures in a rock mass is not random. Joints, the simpler, more regular fractures, often developed in parallel sets, tend to form in systematic orientations controlled by the regional stress field of the surrounding geology. In many parts of the Ozark Plateau, two dominant joint sets exist, oriented roughly perpendicular to each other, the result of tectonic stresses acting on the rock mass from different directions at different times in its history. When groundwater moves through a rock mass cut by two perpendicular joint sets, it follows those joints, and the passages it carves tend to reflect their geometry. This is the key to understanding one of the most striking features of Ozark cave systems, and of karst cave systems generally. Passages that follow joints are straight, or very nearly so. A joint is a planar feature, a flat surface cutting through the rock. When water moves along a joint, dissolving it wider and taller over time, the resulting passage inherits the geometry of the joint. It runs in a straight line. It has flat walls, the walls of the original fracture surface, and a cross-section that tends toward rectangularity, because the rock is being dissolved evenly from both sides of the fracture and from above. And when two perpendicular joint sets control the development of a cave system, the resulting network of passages tends toward a rectilinear plan. Passages running in two primary directions, meeting at right angles, creating a grid-like pattern that to the human eye looks remarkably like the layout of a planned structure. This is geology, not architecture, not engineering, not intention. But the resemblance to intention is real, and it is worth taking seriously as a genuine perceptual experience, because understanding why the cave looks designed is more interesting and more truthful than simply asserting that it is or is not. The dissolution of limestone is not a uniform process. Water that moves through a fracture dissolves the rock most aggressively where the flow is fastest, where turbulence is highest, where fresh, unsaturated water contacts the rock most frequently. Over time, the larger conduits in a developing cave system capture more and more of the available groundwater flow, growing at the expense of smaller passages. This process, called speleogenetic competition, tends to produce cave systems with a relatively small number of large, well-developed passages and a much larger number of smaller, incompletely developed ones. The large, well-developed passages in a mature karst system are often remarkably regular in their cross-section. Flowing water, given enough time, rounds the floor of a passage, sculpting it into a smooth curve called a canyon cross-section in fast-flowing sections, or filling it with sediment in slower sections, leaving a flat floor. The ceiling of a passage carved in well-bedded limestone tends to follow a bedding plane, the flat, horizontal contact between two layers of rock, producing a ceiling that is remarkably even and flat. The walls follow the joints. The result is a passage that is tall, straight-walled, flat-floored, and flat-ceilinged, a passage that, in the beam of a headlamp, looks very much like a corridor. Water does not need a blueprint to produce these forms. It needs time, chemistry, and rock with the right structural properties. And in the Ozark Plateau, it has had all three in abundance for an immensely long period. The underground rivers of the Ozark region are not metaphorical. They are real rivers, flowing water, with measurable discharge rates, responding to rainfall events, carrying sediment, supporting ecosystems, and discharging into surface streams and rivers through springs. Some of these underground rivers are substantial. The groundwater system feeding Mammoth Spring in Arkansas, one of the largest springs in the United States, discharging on average around 235 million gallons of water per day, drains a karst basin of considerable size, moving through cave conduits that have not been fully mapped. Dye tracing, the technique of introducing a non-toxic fluorescent dye into the groundwater at one point and detecting it at springs downstream, has been used extensively in the Ozark region to characterize groundwater flow paths and to connect surface drainage inputs to specific springs. These studies have confirmed that groundwater in the Ozark karst travels remarkable distances underground, sometimes crossing beneath surface drainage divides, sometimes moving in directions that seem counterintuitive from the surface topography. The underground and the surface are connected, but they do not always follow the same rules. The Ozark Aquifer, the system of pores, fractures, and cave conduits through which groundwater moves beneath the plateau, is one of the most important freshwater resources in the region. Communities in southern Missouri and northern Arkansas depend on it for drinking water. Farmers use it for irrigation. The springs it feeds support remarkably diverse ecosystems. Some of the highest quality cold water streams in the central United States, supporting rare fish and mussels and amphibians that depend on the clean, cold, stable flows that karst springs provide. Understanding how that aquifer works, how water moves through it, where it comes from, how it is recharged, how vulnerable it is to contamination from surface activities, is not simply an academic exercise. It is a matter of practical importance for the communities that depend on it. And that understanding begins with the caves, with the passages and conduits that form the plumbing of the system, that carry the water from where it enters the ground to where it emerges. And those passages, those straight, joint-controlled corridors, those flat-floored rooms, those right-angle intersections, are what we will return to again and again as our journey through the Ozark Labyrinth continues. Because the question we began with, why do these passages appear almost designed, is not a question with a simple answer. It is a question that takes us through geology and hydrology and archaeology and human perception, through the history of exploration and the science of modern cave research. And it is a question worth taking slowly. The underground rivers of the Ozarks have been flowing for millions of years without any particular hurry. We can afford to follow them at the same pace. Long before any map was drawn of the Ozark Plateau, long before any European eye looked out across these forested ridges and cedar glades, long before any name was given to these hills in any language that has survived to the present, people were here. They came at the end of the last ice age, or perhaps even before its final retreat, moving through a landscape that was different from the one we know today. The climate was cooler and wetter. The forests were different in their composition. Spruce and fir grew at lower elevations than they do today, mixed with the oaks and hickories that would eventually come to dominate the region as the climate warmed. The rivers ran cold and clear, fed by the melting of glacial ice to the north, and the springs that emerged from the limestone bluffs were, if anything, even more plentiful than they are now. The people who moved through this landscape in those ancient times are known to archaeologists as Paleoindians, a broad term for the earliest human inhabitants of the Americas, people who were fully modern in every biological sense, possessed of the same cognitive capacities, the same social complexity, the same capacity for language and art and spiritual life as any people who have lived since. They were not primitive in any meaningful sense. They were people solving the practical and existential problems of existence in a world that was, in many respects, more challenging than the one we inhabit. Archaeological evidence of Paleo-Indian presence in the Ozark region is real, though it is sparse by the standards of later periods, as is typically the case for the earliest human occupation of any region. Small, mobile groups of people moving through a large landscape leave fewer traces than settled communities. The traces they do leave are often found in specific, favorable locations, places where the landscape offered particular advantages. The bluff shelters of the Ozark region are among the most important of those locations. A bluff shelter is a naturally occurring overhang of rock, a place where a limestone or dolomite cliff has eroded in such a way that a protected space exists beneath the overhang, open to the air on one side, but sheltered from rain and wind by the rock above. The Ozark region has many such features, carved by the same processes of erosion and dissolution that created the caves below. Bluff shelters are dry. They are cool in summer and relatively sheltered in winter. They offer an elevated view of the valley below and the stream that often runs along its floor. They are, in short, extremely practical places to stop, to camp, to shelter for a season. People recognized this immediately, and they have been using bluff shelters in the Ozark region for a very long time. Some of the bluff shelters in Arkansas and Missouri have been excavated by archaeologists, and what those excavations have revealed is a remarkably deep and continuous record of human habitation. At sites like Rogers Shelter in Missouri, one of the most extensively studied Ozark archaeological sites, excavations have produced evidence of occupation spanning thousands of years, from the Archaic period back toward the earlier margins of human presence in the region. The sediments in these shelters accumulated slowly, layer by layer, each layer preserving the materials left by the people who camped there: stone tools, fire hearths, animal bones, plant remains, the debris of daily life. Stone tools are among the most durable and informative materials the archaeological record preserves. The Paleoindian and archaic peoples of the Ozarks made tools from the chert, a fine-grained, flint-like rock that outcrops throughout the region. Ozark chert is varied in quality, and the best quality chert sources were evidently known and valued. Archaeological studies of tool stone distribution show that high-quality chert moved across the landscape in patterns that reflect both the mobility of individual groups and the existence of trade or exchange networks connecting different communities. The presence of tool stone from distant sources at Ozark sites suggests that the people of this region were not isolated. They were connected to communities in other river valleys, to trade networks that brought exotic materials from distant sources to the broader world of prehistoric North America. A piece of chert from a source hundreds of miles away, found in an Ozark bluff shelter, is not just a tool. It is a record of connection, of movement, of exchange, of relationships between people across a landscape that from the air might look empty, but was in fact threaded with human pathways. The Archaic period in the Ozarks, spanning roughly from 10,000 to 3,000 years ago, represents the longest and in some ways richest chapter of the prehistoric human story here. Archaic peoples were hunters and gatherers, moving seasonally through the landscape in response to the availability of food resources. But they were not purely nomadic in the sense of constant, directionless movement. They had seasonal rounds, predictable patterns of movement between locations that offered different resources at different times of year. A spring camp near a productive fishing location on a major river. A summer camp on a high ridge where deer were concentrated and the breeze kept the insects at bay. A fall camp near a productive hickory or black walnut grove. A winter shelter in a bluff overhang where the rock above kept off the snow. The caves and shelters of the Ozark karst fit naturally into these seasonal rounds. People used them for shelter, for storage, and possibly for purposes that went beyond the purely practical. Archaeological evidence from cave sites in the Ozark region, charcoal from ancient fires, stone tools, animal bones, confirms that caves were regular features of the human landscape here, not exotic destinations, but familiar parts of a territory that was intimately known. Fire is one of the most consistent markers of human presence in the archaeological record, and the Ozark cave and bluff shelter sites are rich in it. Hearths, concentrations of charred wood, fire-cracked rock, and ash appear throughout the excavated sequences, some of them radiocarbon dated to ages of several thousand years. The fires that burned in these hearths cooked food, provided warmth, drove away insects, and gave light, and their carbon remains, preserved in the cool, dry conditions of bluff shelters and cave entrances, have been essential in establishing the timeline of human presence in the region. The people who built those fires left other traces as well. Ground stone tools, manos and metates used to process plant foods, appear in the archaic levels of many Ozark sites, reflecting the increasing importance of plant foods in the diet over time. Bone tools, awls, needles, and other implements speak to the working of hides and the making of clothing. Shell ornaments, some of them from marine species that could only have come from the Gulf Coast, confirm the existence of long-distance exchange networks. And in some cave sites, there are traces of something less easily categorized, marks on walls, deposits that seem more deliberate than ordinary camp debris, arrangements of objects that suggest purposes beyond the purely practical. The interpretation of such traces is always difficult and always contested among archaeologists. Not every mark is symbolic, not every unusual deposit is ceremonial. But the possibility that some of these cave sites were used for purposes that went beyond shelter and resource extraction, that they were places of significance in a broader cultural and spiritual landscape, is one that serious researchers take seriously. What those purposes were, specifically, we cannot know with certainty. The archaeological record preserves things and arranges them in patterns that we can observe and analyze. What it cannot preserve is meaning, the frameworks of understanding, belief, and practice that gave those things their significance to the people who left them. For that, we must turn to the living traditions of the peoples whose ancestors inhabited this landscape, and we must do so with the care and respect those traditions deserve. It is also important to be clear about what archaeology cannot tell us. It cannot tell us what language the archaic peoples of the Ozarks spoke. It cannot tell us what they believed about the caves they entered, or the springs that emerged from the limestone, or the underground rivers they could hear but not see. It cannot tell us whether they understood the underground as a practical resource, a sacred space, a dangerous territory, or some combination of all of these. Those questions, the most deeply human questions, are the ones that the physical record alone cannot answer. And they are, perhaps, the questions most worth sitting with. Before we enter this chapter, we need to say something clearly and to hold on to it throughout everything that follows. The indigenous nations whose histories are connected to the Ozark region are not interchangeable. They are distinct peoples, with distinct languages, distinct traditions, distinct histories, and distinct relationships to the landscape. The Osage Nation, the Quapaw Nation, the Caddo Nation, and other peoples who have lived in or moved through this region, each carry their own body of knowledge about the land, knowledge that has been shaped by their own particular histories, their own intellectual and spiritual traditions, their own long experience of this specific landscape. To speak of these peoples as though they shared one common tradition one unified indigenous understanding of the Ozark landscape would be inaccurate, disrespectful, and intellectually dishonest. Different nations preserved different histories. Different nations understood the landscape in different ways. And any attempt to flatten that diversity into a single narrative does a disservice to all of them. With that said, and held firmly in mind, there are some things we can say about the relationship between these specific peoples and the specific landscape we have been exploring. The Osage Nation, whose ancestral homeland encompassed a large territory in what is now Missouri, Kansas, Arkansas, and Oklahoma, maintained one of the most complex and thoroughly documented systems of traditional knowledge about the landscape of the central interior of North America. Osage cosmology. As documented by scholars including Francis La Flèche, who worked with Osage community members in the late 19th and early 20th centuries to record traditional knowledge in unprecedented detail, understood the world as a structured and meaningful place. A place in which the relationships between human beings, the natural world and the spiritual dimensions of existence were carefully ordered and maintained through ceremony protocol and the transmission of specialized knowledge across generations. Water, in Osage tradition, held profound significance. The great springs that emerge from the Ozark limestone, cold, clear, constant, emerging from the rock as though from another world, were not understood as simply hydrological features. They were understood as places where different dimensions of existence came into contact, where the world beneath the surface and the world above it communicated with each other. The Osage term for their most sacred places reflects an understanding of landscape as spiritually animated, not in the vague general sense that sometimes gets attached to indigenous traditions in popular representations, but in a specific, carefully elaborated sense that was the product of generations of intellectual and spiritual refinement. The Osage were a people of the tallgrass prairie and the forest edge. They ranged across a territory that included both the open grasslands to the west and the forested uplands of the Ozark Plateau to the east. Their knowledge of this landscape was intimate and multigenerational, and it encompassed the underground as well as the surface. Caves and springs appear in Osage oral traditions as significant features, the places associated with particular stories, particular beings, particular dimensions of experience that the surface world alone could not provide. It would be inappropriate to describe these traditions in detail here. Much of Osage ceremonial knowledge is not public, and its transmission is the province of the Osage Nation itself, not of documentary narration. What we can say with confidence is that the Osage understood the Ozark landscape as a meaningful place, a place in which the underground, with its rivers and its darkness and its springs, was not separate from the world of human life, but deeply connected to it. The Quapaw Nation, the Ogaxpa, as they call themselves, whose traditional homeland was centered along the Arkansas River at its confluence with the Mississippi, also has historical connections to the Ozark region. The Quapaw were in contact with European explorers beginning in the 17th century, and their traditions and history are documented through a combination of their own oral knowledge and the records of French missionaries and explorers who encountered them. Their understanding of the landscape they inhabited, including the springs and rivers of the Ozark Karst, was shaped by their own distinct intellectual and spiritual framework, one that cannot be merged with Osage tradition without doing violence to both. The Caddo Nation, whose ancestral territory extended across what is now southwestern Arkansas, northwestern Louisiana, eastern Texas, and southeastern Oklahoma, represents yet another distinct tradition. The Caddoan cultural sphere, which encompassed several related but distinct peoples, was one of the most complex and sophisticated in the southern interior of North America. Caddoan peoples built platform mounds, maintained long-distance trade networks, and developed agricultural systems that supported substantial sedentary communities. Their engagement with the Ozark landscape, particularly its southern margins in Arkansas, is documented archaeologically through the presence of Caddoan-style ceramics and other materials at sites in the region. The Caddo maintain traditions about the underground and about springs and rivers that reflect their own long engagement with a karst landscape. The southern Ouachita Mountains and the Arkansas River Valley country share some of the karst characteristics of the Ozark Plateau proper. And water, in its surface and underground forms, figures prominently in Caddoan ceremonial and cosmological tradition. Here again, the specific content of these traditions belongs to the Caddo Nation, not to outside narration, and we note their existence and their depth without claiming to speak for them. What connects these different traditions, not as evidence of a single shared belief system, but as a shared pattern of human response to a particular kind of landscape, is the recognition that underground water has significance. Springs emerging from rock, constant and cold and clear, have moved people across cultures and across centuries to ask questions about what lies beneath, and to develop frameworks, ceremonial, intellectual, narrative, for understanding the relationship between the seen and the unseen. This is not surprising. It would be more surprising if it were otherwise. Springs are genuinely remarkable phenomena. They emerge from solid rock. Their water is cold when the surface world is hot. They flow steadily when surface streams run dry in drought. They are, in the most literal sense, the product of a world that is hidden, a world of underground rivers and passages that most people, for most of human history, could not observe directly. The cultural significance that multiple indigenous peoples have attached to springs and underground water in the Ozark region is in part a reflection of the genuine strangeness and power of these features. The way they seem to offer access to something beneath the surface of the world. Something that operates by different rules, something that deserves attention and respect. Today, the descendant communities of these nations, the Osage Nation in Oklahoma, the Quapaw Nation in Oklahoma, the Caddo Nation of Oklahoma, maintain their traditions and their relationships to the landscapes of their ancestral territories, even at the distance that forced relocation imposed. Tribal historic preservation offices are active participants in the management of public lands in the Ozark region, working to ensure that archaeological materials found on those lands are treated as the heritage of living communities. Consultation with these communities is part of responsible land management in the Ozark region. And the knowledge they bring to those consultations, knowledge of place of history, of the significance of specific landscape features, enriches the broader understanding of the region in ways that purely scientific approaches cannot replicate. The sacred springs and hidden places of the Ozark Plateau belong, in the most important sense, to the peoples whose ancestors first recognized their significance. That recognition preceded any map, any geological survey, any documentary script by thousands of years. It is worth holding that knowledge quietly as we move forward. The first Europeans to enter the Ozark region arrived not from the east, as the dominant narrative of American history might suggest, but from the south, from the French colonial settlements along the lower Mississippi River and the Gulf Coast, moving northward along the Great River and its tributaries in the early 18th century. French exploration of the interior of North America was driven by a combination of motives familiar from the history of European colonialism. The search for trade, particularly the fur trade, the ambition to establish political and territorial claims, the desire to convert indigenous peoples to Catholicism, and the straightforward curiosity of individuals who found themselves on the edge of an enormous and largely unknown continent and wanted to know what lay beyond the horizon. The Mississippi River was the great highway of this exploration. Canoes and pirogues moved up and down it, carrying French traders and missionaries and soldiers and officials into the interior. The Arkansas River, joining the Mississippi from the west, provided a route into the southern Ozark region. The Missouri River, entering from the northwest, opened the northern approach. And at the confluences of these rivers, where the French established posts and communities and trading relationships with the indigenous peoples they encountered, knowledge of the interior began to accumulate. French maps of the interior of North America from the late 17th and early 18th centuries are remarkable documents, remarkable both for what they show and for the particular character of their inaccuracies. The river systems are often recognizable because rivers are the routes that explorers followed and described. The interior is hazier, mountains appear in approximately the right places, but with shapes and scales that reflect estimation rather than measurement, and the relationships between river systems are sometimes significantly distorted. The Ozark region appears on these early maps as a highland, the Montagnes des Ozarks, the mountains of the Ozarks, but its internal geography, its caves and springs and karst features, is essentially unknown to the mapmakers. What the French knew of the Ozark interior they learned primarily from the indigenous peoples they traded with, from Osage hunters and trappers who ranged through the region and who had, of course, a far more detailed and accurate knowledge of its geography than any European explorer of the period. The rivers, the springs, the caves, the routes through the forest, all of this knowledge was indigenous knowledge first, acquired through generations of careful observation and transmitted through the oral traditions and practical education of communities who depended on this landscape for their survival. French lead miners were among the earliest European visitors to penetrate the Ozark interior with any regularity. The Ozark region, particularly in what is now southeastern Missouri, contains significant deposits of galena, the primary ore of Leyde, and French colonial interests recognized the economic potential of these deposits early. Mining operations were established in the region in the early 18th century, making the Missouri Ozarks one of the earliest sites of systematic mineral extraction in the interior of North America. The miners who worked these operations went underground, not into natural caves in most cases, but into shafts and adits they dug themselves, following the veins of galena through the limestone. In doing so, they occasionally intersected natural cave features, passages and chambers carved by water, which their excavations had broken into. The discovery of natural underground spaces in the course of mining was commonplace in the limestone country of the Ozarks, and the miners who encountered them left records, sometimes informal reports to colonial authorities, sometimes in the informal accounts that circulated among the communities of the region. These records are fragmentary and not always reliable. The accounts of miners tend toward the practical rather than the descriptive, and the details that would be most interesting to a modern geologist or cave scientist are often precisely the details that were not recorded. But they represent some of the earliest European documentation of the cave features of the Ozark region, and they establish that the underground character of the Ozark limestone was recognized from the earliest period of European involvement in the region. The American period of Ozark exploration began in earnest following the Louisiana Purchase of 1803, which transferred a vast territory, including the Ozark region, from French to American sovereignty. The new federal government moved quickly to organize expeditions to assess and document the resources of its new acquisition. Among the most important of these early American scientific expeditions in the Ozark region was that led by Henry Rowe Schoolcraft in 1818 and 1819. Schoolcraft, a geologist and explorer who would later become famous for his extensive work documenting the culture and language of Great Lakes indigenous peoples, traveled through the Ozark region of Missouri and Arkansas on foot, and by canoe observing and recording its geology, its natural history, and its human inhabitants with a thoroughness unusual for the period. His published account of the journey, scenes, and adventures in the semi-alpine region of the Ozark Mountains is one of the earliest and most detailed descriptions of the Ozark landscape by a scientifically trained observer. Schoolcraft wrote about the springs he encountered with genuine appreciation for their geological interest. He noted the limestone character of the region, the abundance of caves and sinkholes, the way the rivers seemed to emerge from the ground rather than simply draining from the surface. He described specific cave features he encountered with enough detail to allow later researchers to identify some of them, and he recorded his observations about the indigenous peoples of the region, the Osage primarily, whose territory he was traversing with the limitations and the particular perspective of a man of his time and background, but with a degree of attention and respect that was not universal among American observers of the period. Schoolcraft's journey was one of scientific observation, not systematic survey. The formal geological and topographic mapping of the Ozark region came later, through the work of the state geological surveys, the Missouri Geological Survey and the Arkansas Geological Survey, which began their systematic work in the mid-19th century and continued through the decades that followed. The Missouri Geological Survey, established in 1853, undertook the first systematic geological mapping of the Missouri Ozarks. Survey geologists traveled the region on horseback and on foot, examining rock outcrops, measuring stratigraphic sections, collecting fossil specimens, and recording the locations of springs, caves, sinkholes, and other karst features. Their reports, published in a series of volumes over the following decades, constitute the foundational scientific documentation of the Ozark region's geology, and they remain important references for researchers today. Cave mapping in the Ozark region during this period was not yet a systematic enterprise. Individual caves were described in geological survey reports, their dimensions estimated, their rock types noted, their formations mentioned with varying degrees of enthusiasm. But the detailed, station-by-station survey work that would eventually produce accurate maps of cave systems had not yet been developed as a standard practice. The cave maps of the 19th century are, by modern standards, rough sketches, valuable as historical records, sometimes accurate in their broad outlines, but not reliable in their details. What those early surveys did accomplish was the establishment of the basic geological framework for understanding the Ozark karst, the recognition that the region's extraordinary abundance of springs and caves was the product of the dissolution of limestone and dolomite by groundwater, and that the underground water system of the Ozark Plateau was both extensive and economically important as a source of drinking water, as a factor in the productivity of the region's agriculture, and as a potential resource for the communities that depended on it. There is, in the journals of the early Ozark surveyors, a recurring note of surprise, a note that has nothing to do with the scientific content of their observations and everything to do with the human experience of the underground. Survey after survey, expedition after expedition. The geologists who descended into the caves of the Ozark region wrote about the strangeness of the experience, the quality of the darkness, the sound of underground water, the unexpected scale of the underground chambers, the way the passages seemed to go on beyond the reach of their lamps. And repeatedly, though they did not always have the geological vocabulary to explain it, they wrote about the regularity, the straightness of the passages, the flatness of the floors, the way the cave seemed, in certain sections, to have been shaped by something more deliberate than the random play of water on rock. They were noticing something real, something that geology would eventually explain. But in the moment of encounter, in the lamplight and the silence, the explanation was not immediately at hand. That moment of encounter, that space between experience and explanation, is where the most interesting questions live, and we are going to spend some time there. There is a moment that every serious cave explorer in the Ozark region describes, sooner or later, in one form or another. You are moving through a passage that you have never visited before. Your headlamp cuts a cone of light through the absolute dark ahead of you, and in that cone, the walls of the cave are pale and smooth, running parallel on either side of you at a consistent distance. The floor beneath your feet is flat, not perfectly flat. There is some irregularity, some sediment in places, some slight unevenness, but broadly, substantially flat. The ceiling above you follows a consistent line, parallel to the floor, perhaps 2.5 or 3 meters overhead. The passage runs straight ahead of you for as far as your lamp can reach, and then it turns, not gradually, not in the slow curve of a river meander, but sharply, a right angle. The passage meets another passage, and the new passage runs perpendicular to the one you have been following, again straight, again with flat walls and a flat ceiling, again extending into darkness for a distance your lamp cannot resolve. You stop. You look around. You are standing at the intersection of 2 perfectly straight passages, meeting at a right angle, in the middle of a limestone formation deep beneath the Ozark Plateau. And something in the human mind, something very deep, very instinctive, very difficult to override, says, this was built. It was not built. In the vast majority of such passages in the Ozark Karst, the explanation for this geometry is geological, and it is thoroughly understood. But the experience of standing at that intersection, in that silence, with that lamp, the experience produces a perception that geology does not immediately dispel. And that perception is worth taking seriously, not as evidence of anything supernatural or ancient and mysterious, but as a genuine human response to a genuine geological phenomenon that has not always been well explained. So let us explain it properly. The regularity of cave passages in the Ozark region, the straightness, the right-angle intersections, the flat floors and ceilings, is, in almost every documented case, the direct expression of the structural geology of the surrounding rock. Specifically, it is the expression of joint systems. Joints, as we discussed in an earlier chapter, are fractures in rock along which no significant displacement has occurred. They are cracks, essentially produced by stress in the rock mass over geological time. In the well-bedded limestone and dolomite of the Ozark Plateau, joints develop in systematic patterns. 2 dominant joint sets, oriented roughly perpendicular to each other, cut through the rock across large areas. When groundwater moves through these rocks, it follows the joints, because joints are the initial pathways of least resistance through an otherwise relatively impermeable rock mass. As the water moves along a joint, it dissolves the rock on both sides, widening the fracture. Over time, over a great deal of time, a narrow crack becomes a passage wide enough to admit a human body. And because the joint is a planar feature, geometrically flat, running in a consistent direction, the passage that develops along it is geometrically regular, straight walls, consistent width, a direction that does not deviate because the joint does not deviate. Where 2 perpendicular joint sets intersect, passages develop along both sets and they meet at right angles. The cave plan that results, when viewed from above on a survey map, looks strikingly like the grid of a planned settlement. Parallel passages running in one direction, crossed at regular intervals by parallel passages running perpendicular. Rectangular rooms at the intersections. A geometry that the human eye, trained by millennia of experience with human-made structures, reads as architectural. Geologists call this pattern joint-controlled or rectilinear cave development, and it is well documented not only in the Ozark region but in karst landscapes around the world. It is not unique to the Ozarks. It is not mysterious. It is the expected outcome of groundwater dissolving a well-jointed rock mass along its natural planes of weakness. Given the right rock, the right joint pattern, and enough time, this is what water produces. The flat floors of many Ozark cave passages have a similarly geological explanation. In passages that carried flowing underground rivers, the water's turbulence and abrasive action, carrying sand and gravel along the cave floor, gradually smoothed and leveled the floor surface over time. In passages where water moved more slowly, fine sediment settled out of suspension and accumulated on the floor, producing a flat, even surface of deposited clay or silt. In either case, the flat floor is a product of water and time, not of deliberate leveling. The flat ceilings of many passages, perhaps the feature most suggestive of deliberate construction to the first-time visitor, are usually the result of the passage developing along a bedding plane. A bedding plane is the contact between two layers of rock deposited at different times, and it represents a natural plane of weakness in the rock mass. When a cave passage develops along a bedding plane, the ceiling follows that plane, and because the original sedimentary layers were deposited horizontally in the ancient sea, the bedding plane is horizontal, and the ceiling that follows it is flat. Flat floor, flat ceiling, straight walls following joint planes. A right-angle intersection at the junction of two joint sets. The result, in the beam of a headlamp, is a passage that looks like a corridor in a building. It is not a corridor in a building. It is a natural feature, explicable by well-understood geological processes, produced by hundreds of millions of years of accumulation and dissolution and fracturing, and the patient movement of slightly acidic water through jointed rock. But the experience of it, the immediate, visceral, perceptual experience, is of something that looks purposeful. This is worth sitting with for a moment, not to mystify it further, but because the gap between perception and explanation is itself interesting. Human beings are, by evolutionary history, extremely good at detecting patterns, and specifically at detecting the patterns produced by intentional agents. We are so good at it, in fact, that we sometimes detect intention where none exists. We see faces in clouds. We hear voices in static. We read design into the products of geological processes that have no designer. This tendency, sometimes called agenticity or pattern recognition bias in cognitive psychology, is not a flaw. It is a feature. It is the same cognitive capacity that allowed our ancestors to detect predators in the rustling of grass, to read the intentions of other people from subtle cues, to anticipate the movements of prey animals from slight disturbances in the environment. It is useful. It has been essential to human survival, but it also means that we sometimes see design where there is only process, intention where there is only physics. The cave passages of the Ozark Labyrinth are one of the most striking examples of this phenomenon in the natural world. Now, having said all of this, having established the geological explanation with appropriate clarity, there is one more thing worth saying. Human beings have, in fact, modified cave entrances and near-entrance zones in the Ozark region. The archaeological evidence for this is real. Bluff shelters were sometimes altered, debris cleared, fire hearths constructed, walls of stacked stone built across openings to provide shelter from wind and weather. In some documented cases, cave entrances show signs of modification, material moved, surfaces altered by ancient occupants. This is not surprising. People who used caves regularly would naturally have made them more comfortable and more practical, just as people make any frequently used space more comfortable and practical. And this is an essential distinction. The evidence for human modification of cave entrances and near-entrance zones is not evidence for the construction of the deep cave passages themselves. No credible archaeological evidence supports the idea that the deep, joint-controlled passages of the Ozark Karst were artificially constructed or significantly modified by ancient human activity. The passages are natural. Their regularity is geological. The modifications, where they exist, are confined to the zones of the cave accessible and useful to human occupation, the entrance areas, the sheltered spaces near the surface. The deep passages were carved by water. And that is, if you allow yourself to really absorb it, more remarkable than any alternative explanation. Not because it is surprising, we have spent 2 chapters explaining exactly how it happened, but because the scale of it, the patience of it, the utter indifference of it, exceeds any human engineering project in its grandeur. Water, dissolving rock, for hundreds of millions of years, producing something that looks, in the lamplight, like a corridor. Nature does not need our assistance to be extraordinary, but why, you might ask, does the question still feel alive? Why does the sense of design persist, even after the geological explanation has been clearly and thoroughly presented? That is a question worth holding for a while longer, because the answer involves not just geology, but the history of human imagination underground, the stories that people have told about these passages in the dark, by firelight, across generations. And that is where we go next. A man goes into the cave and does not come back. He was a lead miner, the story says, working a claim somewhere in the limestone hills of the central Ozarks. He had found a passage, a natural one, breaking off from the end of his mine shaft that seemed to go deeper than it should have. He told his partner he was going to follow it a little ways just to see where it went. He took his lamp and he went in. 3 days later, his partner organized a search. They went into the passage as far as they dared, farther than was wise, some of the searchers said afterward, and found nothing. No lamp, no tools. No sign of the man at all. Just the passage continuing ahead of them, straight and dark and silent, going on beyond the reach of any light they carried. This story, or something very much like it, has been told in the Ozark region in more versions than can be counted. The details change. The name of the miner changes. The location shifts from one county to another, from one generation to the next. But the essential shape of the story remains consistent. A man follows a passage into the underground and is swallowed by it. The darkness takes him. The cave, which seemed finite and manageable from the outside, proves to be something else entirely from the inside. This is folklore. It is not a historical record. It is not archaeological evidence. It is a story shaped by the experience of a landscape in which deep, dark passages genuinely do exist, in which a person genuinely could become disoriented and lost in the wrong conditions, and in which the underground has always carried an atmosphere of the unknown that invites narrative. Let us be clear about that before we go any further. The legends of the Ozark underworld are not evidence of hidden civilizations, lost worlds, or ancient engineering projects. They are evidence of something equally interesting and considerably more verifiable: the human imagination responding to a genuinely extraordinary landscape. They are folklore, regional, vivid, deeply atmospheric, and worth knowing on their own terms, as long as we do not mistake them for something they are not. The tradition of Ozark underground folklore is a rich one, and it draws on several distinct streams of narrative that have flowed together over the centuries. The Lost Mine story is one of the oldest and most persistent. The Ozark region has genuine mining history: lead mining in Missouri, zinc mining in Arkansas, and various other mineral extraction operations that have been active since the early colonial period. Real mines exist. Real miners have worked in them, sometimes under dangerous conditions, sometimes encountering unexpected natural features in the course of their work. This historical reality provides the factual foundation on which the folklore builds and then dramatically extends. The lost mine of legend is not the ordinary working mine of history. It is a mine that was found once by someone specific: a Spanish explorer, a French trapper, a Confederate soldier hiding gold from Union troops, and then lost again, its location unknown, its contents fabulous. Variations on this story appear throughout the Ozark region with remarkable consistency. The Spanish explorers who feature in many versions are sometimes historical figures. Hernando de Soto's expedition of the 1540s did pass through the general region, though the details of its route remain debated among historians, and sometimes purely legendary ones whose presence in the narrative owes more to the tradition of Spanish treasure stories common across the American interior than to any documented historical event. The Lost Mine legend serves a specific narrative function. It accounts for the existence of underground passages that seem, to the person who finds them, too large and too regular to be entirely natural, and it provides an explanation for why they are not widely known. The mine was worked in secret. The miners were killed or driven away before they could tell anyone. The entrance collapsed, or was concealed, or is hidden behind a waterfall or a thicket of vegetation that looks exactly like everything around it. This narrative logic is internally coherent and emotionally satisfying, which is precisely why it persists. It does not require any external validation because it accounts for its own unverifiability. The reason there is no evidence, the story explains, is that the evidence was deliberately concealed. This is the structure of legend, not of history. History leaves evidence. Legend accounts for its absence. The tradition of phantom lights in the Ozark underground is another persistent strand of regional folklore. Stories of lights seen in cave entrances at night, flickering, moving, vanishing when approached, have circulated in the region since at least the 19th century. These stories take many forms. Sometimes the light is attributed to the lamp of a lost miner still searching for the way out. Sometimes it is connected to indigenous burial practices, a connection that is almost always speculative, and that reflects the widespread but generally inaccurate association between caves and burial in popular understanding of indigenous cultures. Sometimes it is simply described as a presence, something that is there and that moves, without any further explanation offered or sought. The natural explanations for lights seen in cave entrances at night are numerous and mundane. Bioluminescent organisms, certain fungi, certain bacteria, do occur in cave environments, though rarely at intensities visible to the human eye at any distance. Fireflies, which are abundant in the Ozark region in summer, can be mistaken for more distant or more mysterious lights in the right conditions. The reflective surfaces of underground water, catching light from an exterior source, can produce unexpected glimmers in cave openings. And the human visual system, operating in low-light conditions, is prone to perceiving movement and luminosity in ambiguous visual stimuli, a tendency that the particular atmosphere of a dark cave entrance late at night is well suited to exploit. These explanations are not dismissals. They are the honest account of what is happening, but they coexist with the stories because stories do not require natural explanations to keep being told. Stories persist because they are satisfying, because they give shape to experiences that feel significant, because they connect individual experience to a larger tradition of meaning-making. The underground kingdom, perhaps the most elaborate form of Ozark cave folklore, is a tradition that appears in various forms across the region. These stories describe vast underground spaces far larger than any cave that has been documented, in which whole communities of people once lived or perhaps still live, communities that have been underground so long that they have adapted to the darkness, that they know the underground as intimately as surface people know the world above, that they emerge occasionally to trade or to observe the surface world and then return to the depths. This tradition has parallels in the folklore of many cultures around the world. It is, in structural terms, a variant of the hollow earth mythology that appears independently in multiple cultural contexts. In the Ozark version, the underground kingdom is sometimes attributed to a pre-Columbian civilization of uncertain identity, sometimes to survivors of a historical catastrophe who retreated underground, sometimes simply to an unnamed other, people who are not quite us, who have found a way to live in the dark. It is important to say clearly that no archaeological evidence supports the existence of underground communities or civilizations in the Ozark cave system. The archaeological record of human use of Ozark caves is real and interesting, as we discussed in an earlier chapter, but it reflects seasonal and periodic use of cave entrances and near-entrance zones by surface-dwelling peoples, not permanent underground habitation by any community. The deep passages of the Ozark Karst are cold, dark, and essentially devoid of the resources, sunlight, plant food, surface air, that human communities require for sustained existence. But the story is not about archaeology. It is about imagination, about the human tendency to people the unknown with versions of ourselves, to project human community and human purpose into the spaces that our knowledge has not yet filled. The underground kingdom of Ozark folklore is a story about the edge of the known world, about the possibility that the familiar and the strange coexist in closer proximity than we usually acknowledge. Strange echoes are another recurring feature of Ozark cave folklore, and here the connection to actual cave acoustics is perhaps most direct. We have already discussed the acoustic properties of cave environments, the way that hard, irregular limestone surfaces reflect sound in complex and sometimes startling patterns, producing echoes that seem to come from nowhere, voices that seem to answer from empty passages, sounds that travel farther than they should or arrive from unexpected directions. In the folklore of the Ozark underground, these acoustic phenomena have accumulated a rich narrative life. The voice that answers from an empty passage is the voice of someone who went in and never came back. The sound of footsteps in a passage behind you, stopping when you stop and starting when you start, belongs to something that follows cave visitors without showing itself. The low, resonant humming that some cave visitors report hearing in certain chambers, a sound that may have a natural source in air movement or water flow, becomes in the folklore the sound of the underground itself, communicating in a language that no one has yet learned to translate. These stories do not need to be true to be valuable. They are the imaginative record of human encounters with a genuinely extraordinary environment, an environment that produces perceptions and experiences that exceed the ordinary range of surface world life, and that therefore generates narratives that exceed the ordinary range of surface world explanation. The buried treasure legends of the Ozark underground are perhaps the most universal form of cave folklore, universal in the sense that virtually every cave landscape in the world has them in one form or another. The specifics in the Ozark version reflect the region's particular history. Confederate gold, hidden from Union troops during the Civil War. Spanish silver, cached by explorers who never returned to retrieve it. Native American ceremonial objects placed in caves for safekeeping and now waiting to be found by the right person at the right moment. None of these stories are supported by documented historical evidence. The Confederate treasury was accounted for at the end of the Civil War, and no credible historical record supports the existence of significant caches of Confederate gold in the Ozark cave system. Spanish explorers did not penetrate the interior of the Ozark Plateau in numbers sufficient to have left significant material deposits, and the historical record of their activities in the broader region does not suggest the kind of mineral wealth that the treasure legends require. The attribution of cave deposits to indigenous ceremonial practice conflates several different things: the real archaeological evidence of indigenous cave use, the folklore tradition of hidden treasure, and a generalized and often inaccurate popular notion of indigenous material culture. But treasure legends, like all good folklore, are not primarily about the treasure. They are about the search, about the possibility that the underground contains something of immense value that has been waiting in the dark for someone to find it. They are about the human impulse to believe that the world holds more than what is immediately visible, that patience and courage and the willingness to go into dark places will be rewarded with something wonderful. In that sense, not as history, but as expression, the treasure legends of the Ozark underground are telling a kind of truth. They are describing the real experience of cave exploration, the experience that every person who has gone into an unmapped passage with a lamp and an open mind will recognize. The sense of possibility, the sense that the next turn might reveal something that no one has seen before. The sense that the world is larger and stranger and more generous than the surface suggests. That experience is real. The treasure, in its most literal form, is not, but the experience that is worth going underground for. In the cold, clear water of an Ozark cave stream, something is moving. It is small, a few inches long, pale as old ivory, almost translucent in the beam of a research diver's light. It moves with the easy, unhurried confidence of a creature that has never needed to watch for predators with eyes, because in this world of absolute and permanent darkness, eyes are not the primary sense. It navigates by pressure waves, by chemical signals dissolved in the water, by the vibrations that other living things produce in the medium around them. This is the Ozark cavefish, Amblyopsis rossi, one of the most fascinating inhabitants of the Ozark cave ecosystem, and one of the clearest examples in North America of what evolution looks like when a lineage is isolated in a radically different environment for a very long time. The Ozark cavefish is found in cave streams across the Springfield Plateau of Missouri and Arkansas, a specific geological formation within the broader Ozark region characterized by particularly well-developed karst. It is a small species, rarely exceeding 5 centimeters in length, pale and eyeless in its adult form. Its eyes begin to develop in the embryo, but are overgrown by skin before the fish hatches, a developmental pattern that reflects the evolutionary history of the species, its descent from surface-dwelling ancestors that had functional eyes, and the gradual reduction of those eyes over the generations as darkness made them metabolically costly and selectively neutral. The Ozark cavefish is listed as a vulnerable species. Its range is limited, its habitat is highly specific, and the quality of the groundwater that flows through its cave habitat is directly affected by land use on the surface above. Because the Ozark karst is hydrologically well connected to the surface, because sinkholes and losing streams move surface water into the cave system with relatively little filtration, contaminants that enter the groundwater above can reach the cave streams where the Ozark cavefish lives with surprising speed and at concentrations that can be harmful. This vulnerability is one of the most important reasons why the conservation of the Ozark karst landscape matters beyond the boundaries of the caves themselves. The Ozark cavefish is not simply an interesting biological curiosity. It is an indicator species, a species whose health reflects the health of the broader groundwater system on which it depends, and on which the communities above it also depend for drinking water and agricultural use. The grotto salamander, Eurycia spelea, is another remarkable inhabitant of the Ozark cave system. Salamanders are, in general, creatures of moist and sheltered environments, the forest floor, the stream bank, the undersides of rocks in cool, clear streams. The cave environment, with its constant moisture, constant temperature, and freedom from surface predators, represents in some respects an extreme version of these preferred conditions. But it also presents challenges, the absence of light, and the severe limitation of food resources that absence entails. The grotto salamander begins its life in the surface streams and springs that feed the cave system. As a larval form, it develops in the sunlit, food-rich environment of the spring run, feeding on the abundant invertebrate life there. As it matures, it moves into the cave interior, where it transforms into its adult form. In this transformation, its eyes, which were functional in the larval stage, when it lived in the light, degenerate. The adult grotto salamander is effectively blind, its eyes reduced to small, non-functional structures beneath the skin. This dual life history, beginning in the light, ending in the dark, is one of the more striking examples of the complex relationship between the surface world and the cave world in the Ozark ecosystem. The grotto salamander is not fully a cave species in the sense that its life begins on the surface, but it is not fully a surface species either. It belongs to both worlds simultaneously, spending its adult life in the permanent dark of the cave interior while depending on the surface environment for the conditions that allow it to develop. The cave ecosystem of the Ozark region is not a sealed system. It is connected to the surface above it through multiple pathways, through the water that flows in, through the organisms that move between the surface and the cave, through the organic material that surface processes deliver into the underground. This connectivity is what makes the cave ecosystem function. Without inputs of energy and organic material from the surface, the cave could not support the diversity of life that it does. Bats are among the most important agents of this connectivity. Several species of bat roost in the caves of the Ozark region, including the gray bat, Myotis grisons, and the Indiana bat, Myotis sodalis, both federally endangered species that depend on caves for roosting and hibernation. These bats feed above ground, catching insects in the forest and over the streams and meadows of the Ozark landscape. When they return to the cave to roost, they carry with them the energy they have gathered, deposited, eventually, as guano on the cave floor. Bat guano is the foundation of a food web that extends through much of the cave ecosystem. It is decomposed by bacteria and fungi, whose activity makes its nutrients available to a succession of other organisms. Cave invertebrates, specialized beetles, mites, millipedes, isopods, feed on the guano and its microbial decomposers. Cave spiders feed on the invertebrates. The entire community of life in the cave's entrance and twilight zones is supported, ultimately, by the nightly foraging trips of the bats above. The decline of bat populations across the Ozark region due to white nose syndrome, the fungal disease that has killed millions of North American bats since its introduction from Europe, has had ripple effects through the cave ecosystems that depended on them. Where bat colonies have declined significantly, the guano inputs that sustained cave food webs have decreased, affecting the invertebrate communities and the broader ecology of the cave. The full extent of these ecological cascades is still being studied, but the pattern is clear enough to be deeply concerning to cave scientists and conservation biologists working in the region. Cave crickets, Pseudophilus species in the Ozark region, play a role similar to that of bats in connecting the cave to the surface. They shelter in the cave during the day and emerge at night to forage on the surface, returning in the morning with energy from the surface environment incorporated into their bodies. Their guano and eventually their carcasses add to the organic material available in the cave, sustaining the organisms that cannot leave the underground to feed. The invertebrate fauna of the Ozark caves is diverse and includes a number of species found nowhere else in the world. Species so specifically adapted to the conditions of particular cave systems that their entire global range consists of a single cave or a small cluster of connected caves. These highly endemic species are, from a conservation perspective, among the most vulnerable organisms on Earth. The loss of a single cave system to contamination, to collapse, to modification of the surface hydrology could mean the extinction of species that exist nowhere else. The calcite formations of the Ozark caves are biological records as well as geological ones. As discussed in the context of Mammoth Cave, the chemical composition of speleothems reflects the conditions prevailing when they were deposited, and those conditions include biological factors. The type and density of vegetation growing in the soil above the cave affects the carbon dioxide concentration of the soil water that eventually reaches the cave, which in turn affects the rate of calcite deposition. Changes in vegetation driven by climate change, by land use change, by drought or flood, are recorded in the chemistry of the formations growing in the caves below. Ozark cave formations are among the subjects of ongoing paleoclimate research. Studies that analyze the isotopic and chemical composition of carefully dated speleothem layers to reconstruct the history of climate and vegetation in the region over the past several thousand years. This research is yielding a picture of significant climate variability in the Ozark region over the Holocene, the current geological epoch, which began with the end of the last ice age roughly 12,000 years ago. Variability that has implications for understanding the relationship between climate and the human occupation of the region over the same period. The microorganisms of the Ozark cave system are among the least known but potentially most significant components of the cave ecosystem. Bacteria and archaea inhabit the cave walls, the cave sediments, and the cave waters in communities that are still being characterized. Some of these microorganisms are chemolithotrophs, organisms that derive energy from the oxidation of inorganic chemicals rather than from sunlight or organic material, and they represent the base of food webs that are entirely independent of the surface world. Sustained not by sunlight, but by the chemistry of the rock itself. Research into the microbial communities of Ozark caves is relatively young as a field, and the results so far suggest a level of diversity and ecological complexity that was not anticipated. Caves that appear to the human eye to be virtually empty, No visible formations, no obvious water, no evidence of the larger organisms we have been discussing may harbor microbial communities of considerable richness and ecological significance. Living on the surfaces of cave walls in thin films called biofilms that are invisible to the naked eye but detectable through microbiological sampling and analysis. The cave is not empty. It never was. From the blind Ozark cavefish navigating by pressure waves in the underground streams, to the grotto salamander making its extraordinary journey from surface light to underground dark, to the bats carrying the energy of the surface world into the depths each morning, to the bacteria metabolizing minerals on the cave walls in the total absence of light. Life has found its way into every corner of the Ozark Labyrinth. It has adapted in ways both elegant and astonishing to the specific demands of the underground environment. It has woven itself into a community of extraordinary complexity and resilience, and it has done so, like everything else in this cave system, through the patient application of fundamental processes over immense spans of time. Water carved the passages, life filled them. And in both cases, the result is something that exceeds, in its beauty and its complexity, anything that a human designer could have planned. On a cool morning in early autumn, a small team of cavers assembles at the entrance to an Ozark cave that most people have never heard of. They are not tourists. They carry equipment that takes a moment to inventory: waterproof survey notebooks, compass clinometers, measuring tapes, laser distance meters, camera systems in protective housings, rope, and the particular kind of focused quiet that belongs to people preparing for work that requires both physical attention and mental precision. Some of them have been here before, many times. Others are new to this specific cave, but experienced in the broader discipline of cave survey. They know how the work goes, they know what to expect from the rock, and they know that what they will find today may or may not match what the last team reported from adjacent passages. They sign the cave register, check their lights, confirm their communication plan for the day, and then they go in. This scene, or something very much like it, repeats itself throughout the Ozark region on weekends and vacation days throughout the year, and sometimes on weekdays too, when academic or government research schedules permit. The people doing this work are speleologists, cave scientists, and the broader community that supports and extends their work includes geologists, hydrologists, biologists, archaeologists, and the skilled volunteers of organizations like the Missouri Speleological Survey and the Arkansas Speleological Survey, whose members have devoted thousands of hours and many years of their lives to the systematic documentation of the Ozark Cave resource. Cave survey in the Ozark region today is conducted using methods that have evolved significantly from the rough compass and estimation techniques of the 19th century geological surveys. Modern cave survey uses precise instruments, a compass and clinometer readings accurate to fractions of a degree, laser distance meters that can measure the distance between survey stations to within a centimeter. Systematic recording protocols that capture not only the geometry of the passage, but its character, the rock type, the nature of the floor and ceiling and walls, the presence of formations, the evidence of water, the condition of any biological or archaeological features. Each survey station is a fixed point in the cave, often marked with a small piece of flagging tape or a survey marker, from which measurements are taken to adjacent stations. The distance between stations, the compass bearing from one to the next, and the angle of inclination, whether the passage slopes up or down between the two stations, are recorded at each step. These measurements, when compiled and processed using cave survey software, produce a three-dimensional skeleton of the cave's geometry, a wireframe model that represents the centerline of each passage surveyed. To this skeleton, additional measurements are added: the distance from each survey station to the nearest wall on each side, to the floor below, and to the ceiling above. These cross-section measurements fill out the wireframe into a more complete representation of the passage, showing its shape and size at each point along its length. The result, when all the data from a survey project is compiled, is a map that represents the cave's known passages with a precision and accuracy that the early geological survey descriptions could not approach. The maps produced by modern cave survey are remarkable documents. They show at a glance the geometry that we have been discussing throughout this documentary: the straight passages following joint systems, the right-angle intersections, the rectilinear plan of joint-controlled cave development. They also show the complexity that simple description cannot fully convey: the way passages branch and merge, the way vertical shafts connect different levels of the cave, the way the overall plan of the cave reflects the geological structure of the surrounding rock in ways that become visible only when you can see the whole system laid out in plan. Several cave systems in the Ozark region have been extensively surveyed, and their maps are among the most detailed underground cartographic documents in the central United States. Marvel Cave in Missouri, the cave beneath Silver Dollar City, known to generations of Ozark visitors, has been surveyed in considerable detail, its passages mapped, and its geological structure analyzed. Blanchard Springs Caverns in Arkansas, a show cave within the Ozark National Forest, managed by the United States Forest Service, has been surveyed and its geology studied as part of ongoing research and management efforts. Onyx Cave, Mystic Caverns, and numerous other smaller systems throughout the region have been surveyed to varying degrees of completeness. But for every cave that has been thoroughly surveyed, there are others that are known only in outline, their full extent and character not yet determined. And there are certainly cave systems in the Ozark region that have not yet been found at all. Systems whose entrances are hidden beneath forest duff or collapsed into sinkholes, whose surface expressions are subtle enough to have escaped detection, whose existence is suspected from hydrological evidence, but not yet confirmed by direct exploration. The detection of unknown cave systems is one of the most challenging problems in karst science, and it is one where modern technology is beginning to offer genuinely new capabilities. LIDAR, light detection and ranging, has transformed the way karst landscapes can be analyzed from the surface. Airborne LIDAR systems, carried on aircraft or increasingly on drones, emit laser pulses toward the ground and record the return time of the pulses reflected from the surface. By processing millions of such measurements, LiDAR produces a digital elevation model of extraordinary precision, a three-dimensional map of the ground surface accurate to within a few centimeters, even in areas of dense vegetation where conventional photography or satellite imagery cannot penetrate the forest canopy. For karst research, LiDAR is transformative. The subtle topographic features of karst landscapes, sinkholes, dry valleys, spring basins, low ridges that reflect underlying joint systems in the rock, are clearly visible in LiDAR data even when they are completely invisible from the ground under forest cover. Researchers analyzing LiDAR data from the Ozark region have identified previously unknown sinkhole fields, confirmed the surface expression of geological structures known from subsurface data, and located potential cave entrances that were not previously documented. This kind of remote sensing analysis does not replace ground truthing, the physical visit to each identified feature to confirm what it actually is. But it dramatically improves the efficiency of the search for new cave entrances and new hydrological connections, allowing researchers to focus their field time on locations where the likelihood of finding something significant is highest. Ground-penetrating radar offers another tool for detecting subsurface voids from the surface. By emitting radar pulses into the ground and analyzing the reflections from subsurface boundaries, ground-penetrating radar can, under the right conditions, detect air-filled voids in the rock, potential cave passages, at depths of several meters below the surface. The technique has limitations. It works best in relatively dry conditions. Its effectiveness decreases with depth. And the signal can be complex and difficult to interpret in highly heterogeneous rock. But it has been used successfully in karst areas around the world to locate subsurface voids before physical excavation or drilling is attempted. Dye tracing remains one of the most powerful and widely used tools for understanding the hydrology of the Ozark karst. The Missouri Department of Natural Resources and various academic and agency research programs have conducted extensive dye tracing studies throughout the Missouri Ozarks, building a detailed picture of groundwater flow paths and travel times across the region. These studies have confirmed hydrological connections between specific sinkholes and specific springs, established the travel times of groundwater through different parts of the karst system, and identified the recharge areas, the surface drainage basins that contribute water to specific springs. The results of dye tracing studies have direct practical implications. They identify which surface areas are hydrologically connected to which springs, information that is essential for protecting the water quality of those springs and the communities that depend on them. They reveal the distances over which groundwater contaminants can travel in the Ozark aquifer, sometimes far greater distances than intuition would suggest, crossing surface drainage divides that would seem to separate one watershed from another, but that mean nothing to the water moving underground through the cave conduits below. Cave diving, the exploration of flooded cave passages using specialized diving equipment, has extended the known extent of several Ozark cave systems into their submerged sections. In the Ozark region, as elsewhere in karst terrain, many cave passages pass below the water table and continue as flooded conduits for unknown distances. The springs that emerge from the base of Ozark bluffs, some of them large enough to be impressive rivers in their own right, are the outlets of these submerged systems, but their full upstream extent is known only where cave divers have been able to penetrate them. Cave diving in the Ozark region is technically demanding and inherently hazardous. The flooded passages of Ozark cave systems often have low visibility due to fine sediment that is easily disturbed, unpredictable flow conditions that can change rapidly after rainfall events, and complex geometry that makes navigation difficult. The divers who work in these conditions are among the most technically skilled and carefully trained practitioners in the broader caving community. They proceed with exceptional caution, laying guidelines as they go, monitoring their gas supply against strict conservative limits, and turning back when conditions change or when their safety margins are approached. Despite these challenges, cave diving explorations in the Ozark region have produced significant results. The submerged passages of some Ozark spring systems extend for considerable distances back into the aquifer, and the mapping of these passages, even partially, has substantially improved the understanding of how groundwater moves through the deeper levels of the Ozark karst. In some cases, cave divers have confirmed connections between cave systems that were previously suspected from hydrological data, but not directly verified. The conservation of the Ozark cave resource is an integral part of the scientific enterprise in this region, not separate from research, but woven through it. The National Park Service, the United States Forest Service, the Missouri Department of Conservation, the Arkansas Natural Heritage Commission, and various other state and federal agencies with management responsibilities for Ozark lands all maintain programs related to cave conservation and research. The caves within Ozark National Scenic Riverways, the National Park Service unit in Missouri that protects a stretch of the Current and Jacks Fork rivers and the surrounding karst landscape, are subject to ongoing scientific study and careful management protocols designed to protect both the physical cave environment and the organisms that inhabit it. One of the most important conservation challenges in the Ozark cave system, as in cave systems everywhere in the eastern United States, is the management of white nose syndrome and its effects on bat populations. Conservation biologists have been working to monitor bat populations in Ozark caves to understand how different species and different roost sites are being affected by the disease, and to evaluate potential interventions that might help bats survive and recover. The human relationship with the Ozark cave system, the relationship we have been exploring throughout this documentary from its ancient beginnings with the Paleoindian and archaic peoples who sheltered in the bluffs and entered the caves, to the indigenous nations who understood springs and underground water as significant features of a meaningful landscape, to the French miners and American surveyors who began to document the underground world in writing, continues today in the form of science. Patient, methodical, collaborative, honest science. Science that is still expanding what is known, still finding new passages and new species and new connections, still sitting with the questions that the cave poses without forcing answers that the evidence does not support. The map of the Ozark Labyrinth grows, carefully, one survey station at a time. And the underground, indifferent to the mapping, continues to be exactly what it is: vast, complex, patient, and inexhaustible in its capacity to reward careful attention. We have traveled a long way to return to this question. We have followed it from the surface of the Ozark Plateau, from the misty cedar glades and the dimpled sinkhole meadows, and the springs emerging cold and clear from limestone bluffs, down through hundreds of millions of years of geological history. Through the lives of the ancient peoples who used this landscape, and gave it meaning through the stories that human imagination has woven around the underground across generations of encounter. Through the science that has been slowly and carefully building a picture of what the underground actually is and how it actually works. Now we return to the question with all of that knowledge in hand. Why do some underground passages in the Ozark Labyrinth appear almost engineered? And the answer, arrived at honestly, supported by evidence, and stated without either sensationalism or dismissiveness, is this: because geology, given the right materials and enough time, produces forms that challenge human expectations about what nature is capable of. Let us be specific. The straightness of joint-controlled cave passages is real. It is not an illusion, not an exaggeration, not a misperception by the people who notice it. In well-jointed limestone, passages that follow joint planes are genuinely, measurably straight over distances that would be remarkable in any human construction project. The geometry is the direct expression of the geological structure of the rock, and it is consistent and predictable wherever the same structural conditions exist. The right-angle intersections of passages following two perpendicular joint sets are equally real. They are not approximately right angles. They are the actual geometric consequence of passages developing along two joint sets that are genuinely perpendicular to each other, which is a common structural feature in many rock masses, including the Paleozoic limestone and dolomite of the Ozark Plateau. When a cave survey map shows a rectilinear pattern of passages meeting at right angles, it is showing the actual geometry of the cave, which is itself a direct record of the joint geometry of the surrounding rock. The flat floors and flat ceilings that complete the corridor-like appearance of many Ozark cave passages are also real and also geological in their explanation. Flat floors produced by fluvial smoothing or sediment deposition. Flat ceilings produced by bedding plane controlled dissolution. These are well-understood processes producing well-understood results. All of this is geology. All of it is explicable by the interaction of water and chemistry and rock structure over geological time. None of it requires or is supported by any hypothesis of ancient human construction or modification. And yet, the question is not entirely without a factual component when it comes to human modification of cave environments. Here, it is important to distinguish carefully between what the evidence shows and what it does not show. The evidence shows that human beings have modified cave entrances and near-entrance zones in the Ozark region. Bluff shelters were improved, cleared, walled, organized for habitation. Cave entrances were used repeatedly over long periods, and the evidence of that repeated use has accumulated in ways that reflect not random visitation, but patterned, intentional activity. In some documented cases, the entrance zones of caves show signs of deliberate modification, the removal of debris, the construction of simple structures, the organization of space for specific purposes. This is not surprising. It is exactly what we would expect from people who used these spaces regularly and practically. People modify the environments they use. It is one of the most fundamental expressions of human intelligence and adaptability. The ancient inhabitants of the Ozark bluff shelters were doing what people do, making a useful space more useful. But the evidence does not show construction of deep cave passages. It does not show large-scale modification of the underground geometry. It does not show the quarrying or shaping of limestone walls to produce the corridor-like passages that prompted our central question. Those passages exist at depths and distances from the surface that were not regularly frequented by ancient peoples in the Ozark region, and they show no signs of tool marks or other indicators of deliberate human shaping. This is where the question resolves, not with a dramatic revelation, but with the quieter and more satisfying conclusion that the evidence supports. The Ozark Labyrinth is extraordinary. Its passages are genuinely remarkable in their regularity and their scale. But that extraordinariness is the product of geology, of the specific combination of rock type, rock structure, water chemistry, and geological time that prevailed in this particular corner of the North American continent over the past several 100 million years. There are also genuine scientific debates worth acknowledging, debates that are not about ancient engineering, but about the relative contributions of different geological processes to the development of specific cave features. Speleogenesis is not a simple, uniform process. Different sections of the same cave system may have developed under different conditions, some under the influence of a free-flowing underground stream, others under slow, diffuse groundwater flow, others perhaps under the influence of deeper, upwelling water with different chemistry. The relative contributions of these different processes to the development of specific passages and chambers is a matter of ongoing scientific investigation, and the answers are not always simple or clear-cut. In some cases, Ozark cave passages show features that suggest formation by processes other than the simple joint-controlled dissolution we have emphasized so far. Dome-shaped ceiling features, called domes or bell holes, that occur in some cave ceilings may reflect dissolution by upwelling water moving under hydrostatic pressure, rather than by a stream flowing at the surface of the passage. Irregular ceiling pockets and scalloping patterns on walls record the flow velocity and direction of ancient cave streams in ways that allow researchers to reconstruct the hydrological history of specific passages. These details of cave morphology are the subject of active research, and they tell a rich and complex story about the history of water movement through the Ozark Karst. None of this complexity changes the fundamental answer to our central question. The passages of the Ozark Labyrinth were not engineered by ancient human hands. They were engineered, if we want to use that word in its most expansive sense, by water. By the extraordinarily patient, extraordinarily consistent application of slightly acidic water to well-jointed limestone over timescales that dwarf the entire history of human civilization. Water is the architect of the Ozark Labyrinth. Time is its construction period. Chemistry is its tool. And the result, the vast, rectilinear, echoing, dripping, living underground world beneath the Ozark Plateau, is something that no human engineer has ever produced, and no human engineer is likely to surpass. Not because human engineers are incapable of impressive work, but because no human construction project has ever had access to the resources that water has worked with here. Hundreds of millions of years, an entire continent's worth of limestone. The inexorable, patient chemistry of dissolution applied without pause, without rest, without any agenda beyond the simple tendency of water to go where it can and to take with it, dissolved, whatever the rock will give. The Ozark Labyrinth is extraordinary precisely because nature is capable of creating forms that often challenge human expectations, forms that look, to the human eye trained by millennia of experience with human-made structures, like the products of deliberate design. The appropriate response to that recognition is not to search for a hidden designer, but to deepen the appreciation of what natural processes, given enough time and the right conditions, are actually capable of. That deepening of appreciation is, perhaps, the most valuable thing that a careful look at the question can offer. There is one final thought worth adding here before we return to the surface. The human tendency to see design in the products of natural processes, the agenticity that leads us to read the corridor-like passages of the Ozark Cave as though they were built, is not simply an error to be corrected. It is also a prompt. A prompt to ask questions, a prompt to go deeper, both literally and figuratively, into the understanding of how the world works. The person who stands at the intersection of two right-angle cave passages and thinks, "This looks designed," and then asks why it looks designed. And then follows that question into the geology and the hydrology and the long history of the Ozark Plateau. That person is doing something genuinely valuable. They are using the perception of apparent design as the beginning of a much richer inquiry. And that inquiry, honest, patient, evidence-based, open to complexity and comfortable with uncertainty, is the best response this landscape can ask of us. The cave does not need us to invent mysteries for it. It has real ones in abundance, and they are more interesting than anything we could invent. The light is changing above the Ozark Plateau. It is late afternoon now. The sun has dropped below the angle where it illuminates the tops of the ridges directly. And the forests are moving into that particular quality of early evening light that is not yet dusk, but is already softer and more golden than the direct light of midday. The shadows of the oaks are long across the cedar glades. The air has cooled, and from the creek bottom below the ridge comes the first tentative song of a wood thrush. One phrase, then a pause, then another phrase, as though the bird is deciding whether it is evening enough to begin in earnest. Somewhere on the valley floor, a spring emerges from the base of a limestone bluff. Its water is cold, 58 degrees Fahrenheit, the same in this golden October evening as it was in January, and as it will be next July, utterly unaffected by the seasons that govern everything on the surface above it. The spring forms a small pool at the base of the bluff, clear and still, and then begins its journey as a surface stream, joining a creek that joins a river that joins, eventually, the Mississippi and the sea. The water that is emerging from that spring fell as rain somewhere on the plateau above, perhaps last week, perhaps last month, perhaps considerably longer ago than that. It entered the karst system through a sinkhole or a permeable soil patch, and it has been moving underground, through passages and conduits carved by the predecessors of this very water over millions of years, making its patient way toward the spring. It carries dissolved in it a small amount of the limestone it has traveled through, calcium and bicarbonate ions, the infinitesimal products of the ongoing dissolution that is, incrementally, still widening the passages below. The cave is still growing, slowly, invisibly, but without stopping, beneath the forest. Beneath the cedar glades and the sinkhole fields and the creek valleys, with their limestone bluffs, the Ozark Labyrinth continues to be what it has always been. A vast three-dimensional world of passage and chamber and underground river carved from ancient seabed by the patient chemistry of moving water. Inhabited by creatures that have adapted over geological time to the specific demands of permanent darkness, visited across thousands of years of human history by people who came with fire and purpose and questions that the cave received without answering. The geological time that made this place is almost impossible to hold in the mind, but it is worth trying, at least briefly, at least as an exercise in perspective. The limestone beneath the Ozark Plateau began its existence as the floor of an ancient sea more than 300 million years ago. The uplift of the Ozark Dome that began the process of exposing and eroding that limestone started tens of millions of years ago. The cave system that water has been carving from it has been developing for millions of years, long before there were human beings anywhere on Earth, long before there were mammals of any kind, long before the Ozark landscape looked anything like it does today. Against that scale of time, the 4,000 or more years of human presence in this landscape is very brief. The few centuries of European-American engagement with it is briefer still. And the decades of systematic scientific study that have produced our current understanding of the geology, hydrology, ecology, and archaeology of the Ozark karst are, in geological terms, a single, almost invisible instant. We are very new here. The cave is very old. And yet this is perhaps the most important thing. The newness of our presence does not diminish the quality of our attention. The Paleoindian hunters who sheltered in the bluffs of the Ozark Plateau 10,000 years ago were paying close attention to this landscape. They had to, their survival depended on it. The Osage hunters who moved through the same landscape centuries later were paying close attention. The French miners and the American geological surveyors who first began to document the underground world in writing were paying close attention. each in their own way, with their own frameworks and their own purposes. And the cave scientists and speleologists who work in the Ozark caves today are paying close attention. The most systematically rigorous and technically sophisticated attention that has ever been directed at this underground world. All of this attention, across all of these generations, has produced something. Not a complete understanding. The cave is too large and too complex for any current understanding to be complete, but a growing, deepening, increasingly nuanced picture of what this place is, how it came to be, and why it matters. The geology is the foundation of everything: the ancient limestone, the uplift and erosion of the Ozark Dome, the karst development that dissolved the rock from within over millions of years, the joint systems that gave the passages their remarkable geometric regularity. Without understanding the geology, nothing else about the Ozark Labyrinth can be properly understood. The geology is not merely background, it is the primary fact, the ground on which all other understanding rests. The water is the artist. It has been working in the dark, on the limestone canvas that the ancient sea provided, for longer than the imagination can easily hold. It has produced passages of extraordinary regularity and chambers of extraordinary scale, formations of delicate beauty, ecosystems of remarkable complexity. It has done all of this without plan, without intention, without any awareness of the result, guided only by gravity and chemistry and the patient, inexorable tendency of slightly acidic water to dissolve the rock it moves through. The result is something that looks, in the lamplight, like the work of a purposeful mind. It is not. It is better than that. It is the work of a universe that does not need intention to produce order, that generates complexity and regularity from the simple, consistent application of physical and chemical laws over time. The Ozark Labyrinth is a lesson in what nature is actually capable of when given enough time and the right conditions, and that lesson is more profound and more humbling than any story of ancient engineering could be. The human presence in this landscape is its own kind of wonder. People came here, across thousands of years, from the earliest Paleoindian hunters, following the great animals of the late Ice Age, to the archaic families who made seasonal rounds through the karst landscape and sheltered in the limestone bluffs, to the indigenous nations who understood the springs and underground water as significant features of a world that was spiritually as well as physically meaningful, to the French miners who went underground in search of lead, to the American surveyors who began the long work of mapping what lay beneath the hills. All of them were drawn here, to the springs, to the bluffs, to the caves, by the same combination of practical necessity and something harder to name. The underground draws people. It has always drawn people. There is something in the encounter with a cave, with the darkness and the silence and the cool, mineral air and the strange, sourceless sounds, that reaches past the practical and into something deeper. Something that makes people stop and look around and ask the oldest question: what is this place? The indigenous peoples who maintain traditions about sacred springs and underground water were answering that question in their own ways, with their own frameworks of understanding. Their answers were not wrong because they were not geological. They were the kind of answers that address dimensions of experience that geology does not reach. The meaning of a spring, the significance of the boundary between the surface world and the underground, the relationship between the seen and the unseen, the known and the unknown, the world we live in and the world that lies just beneath it. Those are real questions. They deserve real consideration, careful, respectful, honest consideration that neither dismisses them as unscientific nor mistakes them for scientific claims. The exploration of the Ozark Labyrinth by the speleologists and cave divers and survey teams who work in it today is a different kind of answer to the same question. It is an answer built from measurement and observation and the patient compilation of data into understanding. It is incomplete, necessarily, honestly, productively incomplete, because the cave is larger than what has been surveyed, and the science is always catching up to the reality. But it is growing, and it is rigorous, and it is producing a picture of the underground world that is both more accurate and more astonishing than any picture produced before it. The map grows, the understanding deepens, the questions evolve. And the cave, vast, patient, indifferent, extraordinary, remains what it has always been, a place carved from ancient stone by water and time, a place inhabited by creatures adapted to permanent darkness, a place that has sheltered human beings and received human curiosity across a span of time that makes the entire recorded history of civilization seem very brief, a place that looks, in the lamplight, like something designed, and that is, in fact, something better than designed. Something produced by the universe's own deep tendency toward complexity and order, working through the medium of limestone and water and an almost unimaginable depth of time. The wood thrush has finished its evening song. The light on the ridgeline has faded from gold to the pale, luminous gray of late dusk. The forest is settling into the sounds of night, the first tentative calls of the whippoorwill from somewhere in the cedar glades, the distant sound of a creek running over limestone in the valley below. And beneath all of it, beneath the darkening forest and the cooling air and the first stars appearing in the deepening blue above the ridge, the underground rivers are still moving. They are moving now, as they have been moving every moment of every day across the whole of geological time that this limestone has been dissolving. The water falls as rain. It enters the karst through the sinkholes and the permeable soils. It moves through passages that took millions of years to carve, guided by joints in the rock that are the record of ancient tectonic stresses, emerging finally at springs that have been flowing since long before any human eye saw them. Drop by drop, passage by passage, year by year. Million by million, the Ozark Labyrinth deepens invisibly in the dark beneath the forest. Passages that are today too narrow to enter are becoming, incrementally, slightly wider. Chambers that do not yet exist are becoming, in the most preliminary and provisional way, possible thin planes of weakness in the rock that water has found and begun, barely, to widen. The cave that future explorers will find is different, very slightly, from the cave that exists today. Nature is patient in ways that we are not. It does not need to finish. It does not need to be understood. It simply continues, as it has always continued, applying the same simple processes to the same ancient materials in the same ancient dark, producing results of extraordinary beauty and complexity that no one planned and no one anticipated. We came here with a question: why does the Ozark Labyrinth sometimes appear almost engineered? We leave with an answer: because geology, given the right materials and enough time, produces forms that exceed what human expectation assigns to nature. Because the joint systems of the Paleozoic limestone and the patient dissolution of slightly acidic water and the structural geometry of the rock itself conspire across millions of years to produce passages of remarkable regularity that the human eye reads as the product of intention. And we leave with something else as well, not just an answer, but an appreciation. An appreciation for what this landscape actually is: not a place where ancient mysteries are hidden and suppressed, but a place where the real mystery is openly on display, in every spring and every sinkhole and every passage carved straight and true through 300-million-year-old stone. The real mystery is this: that the universe, following nothing but its own consistent laws, produces wonders. It always has, it always will. The sound of underground water reaches you faintly from somewhere below the surface, a soft, continuous sound barely audible above the whisper of wind in the oaks. It is the sound of the cave continuing its long, patient, extraordinary work. It is the most peaceful sound in the world. Good night, if you found yourself drifting somewhere in the cedar glades of Chapter 2, or somewhere along the underground river in Chapter 3, or somewhere in the lamplight of a joint-controlled passage in Chapter 7, we hope you slept well. The Ozark Labyrinth will be here when you wake up, still dissolving, still deepening, still flowing in the dark beneath the forest, patient and indifferent and extraordinarily beautiful. Sweet dreams.